Good day, everyone. We, the Brave Hearts, would like to present to Dr. Rosemary G. Felimon our output for Block 1 in real analysis. Before we proceed to the presentation, let me introduce the members of the group. We have Michelle Dordas, Shane Esquilio, Ofelia Aljaid Ramos, Lori Sabando, and Mayflower Bigapria. Getting real with real numbers. So what are real numbers? So real numbers are visualized as a line, and each point on this line represents real number. And a point might be a rational or irrational number. So real number can be defined as union of both rational and irrational numbers. So suppose you split the real numbers so that the entire set R is split into two subsets such that one subset is to the left of the splitting point that can cause this partition. So then the real line is continuous. So this is how we equate the real numbers to a continuous line. So if you can split the line into two such classes, then there is only one point which causes the split. Dedekind cut consisted in separating all the real numbers in a series into two equal parts, such that each real number in one part is less than every real number in the other. The set of real numbers consists of different categories such as natural and whole numbers, integers, rational and irrational numbers. So in the table given on the next slide, so all the real numbers formulas, so the representation of the classification of real numbers are defined with examples. So in this table, we have to define and give example for each category. So first, we have the natural numbers. It contains all counting numbers which start from 1. So for example, all numbers such as 1, 2, 3, 4, 5, 6, and so on. Next, we have whole numbers, collection of zero and natural numbers. So example, all numbers including 0 such as 0, 1, 2, 3, 4, 5, and 6. Also, we have integers, the collective result of whole numbers and negative of all natural numbers. It includes negative infinity. We have -4, -3, -2, -1, and also it includes 0 and 1, 2, 3, 4 up to positive infinity. Next, we have rational numbers. Numbers that can be written in the form of P over Q, where Q is not equal to 0. So for example of rational numbers, we have 1/2, 5/4, and 12/6, etc. Last, we have here the irrational numbers, the numbers which are not rational and cannot be written in the form of P over Q. And irrational numbers are non-terminating and non-repeating in nature, like square root of 2.
We begin with a brief discussion of the algebraic structure of the real number system. In the terminology of abstract algebra, the system of real numbers is a field with respect to addition and multiplication. When we speak of field, a set F of two or more elements together with two operations called addition and multiplication is a field if it satisfies the following actions. As you can see, I have here the code of A, A1, A2, and A3, which stands for addition. So we have here the first axioms for field. For all or for every element of A and B belongs to F, there exists a unique element called their sum. A plus B belongs to F. And this property is called closure under usual addition. So when you speak of closure, closed on an operation means that when we perform that operation on a set, the result is still inside the set. Then we have the next one. We have element A, B, and C, which is an element of F, such that the sum of A plus B and plus C is equal to A plus the sum of B plus C. And this law is what we call the associative law or the associativity. Then the next one, we have there exists an element which we denote by 0 such that A plus 0 or 0 plus A is equal to A plus 0 is equal to A for all A is an element of F. And this what we call the identity property of addition. Then we have this A4. So we have there for every A, an element of F, there exists an element which we denote by negative A, such that A plus negative A or is equal to negative A plus A is equal to 0. And this is what we call the inverse property of addition. Then we have this A and B, which is an element of F, such that A plus B is equal to B plus A. And this property is what we call the commutative law, or this property is the basis of the group and is also known as the abelian or commutative group. Then let's move on to the next property, and we have here M stands for multiplication. So for every or for all element A, B, which is an element of F, there exists a unique element called their product, which denote by AB or A times B. So this property or this axiom stands for closed under usual multiplication. Then we have the next one. This is what we call the associative law under multiplication. We have here A, B, C, which is an element of F, such that the product of A and B multiplied to C is equal to A multiplied to the product of B and C. And then we have here, there exists an element different from 0, which we denote by 1, such that A multiplied to 1 is equal to A multiplied to 1, which is equal to A. For all A is an element of F. And this is what we call the identity property of multiplication. The next is, we have here for each A an element of F. A, which is not equal to 0, there exists an element which we denote by the inverse of A, such that A times its inverse is equal to 1. And this is what we call the inverse property of multiplication. The last here for multiplication, we have the commutative law. So we have A and B, an element of F such that A times B is equal to B times A. And we have here for the last axioms, we have the distributive law. As you can see, we have here the left distributive law and we have here the right distributive law. So multiplication is distributive with respect to addition. And that's all for the field axioms.
Now I will be sharing with you the principle of mathematical induction. So we are familiar with this principle since we have this in our number theory. So we have learned it already. So let us go back and let us try to find an analogy or to make an analogy of the principle of mathematical induction. So the principle of mathematical induction, as we know, is a technique of proving a statement, also a theorem or a formula, which is thought to be true for each and every natural number represented by small letter n. So this is a specific technique that we have been using to prove certain statements, usually in algebra, which are formulated in terms of n. Any mathematical statement or expression is proved based on the premise that we are using. So n equals 1 and n equals k, then it is proved for n equals k plus 1. So going back to the technical definition of mathematical induction, suppose that P of n is a statement involving the positive integer n. So, and also let us suppose that these two conditions are satisfied. First, P sub 1 is true. So that is n equals 1. And number two, if k is an arbitrary positive integer for which p sub k is true, then p sub k plus 1 is also true. That is, whenever the statement is true for n equals k, then we can say that it is also true for n equals k plus 1. So the statement p sub n then is true for all positive integer values of n. This is the summary. So we prove that the p of 1 is true, so n equals 1. Then we assume that the p of k is true, n equals k, and we prove then that we go to our proof that the p of k plus 1 is true. Okay, so let us think of this analogy. Let us consider this principle that is analogous to setting domino chain reaction. In this chain reaction, we only need to hit or to knock off one of the pieces of the dominoes to start the chain reaction. So let us think of these pieces of these dominoes as natural numbers. So a line of natural numbers. So to make the dominoes move, any domino can be knocked off for a start. Then it will knock off the domino next to it, and then that domino also will knock the one next to it, then the next, and then the next up to the last domino standing. But are we sure that when we push to knock off one domino, it will knock off the next one? So in this analogy, if these dominoes are natural numbers, how sure are we that when we take a number as a premise, it will hold true for a statement that we want to prove? Okay, so let us check. So let us assume that those dominoes there are the P of 1, P of 2, P of 3, and so on. So assuming that the infinite lines of these dominoes here are the P of 1, P of 2, P of 3, and so on. Then let us have this assumption. If the P of 99 is knocked over, it will knock over P of 100. So if the 99th domino is knocked over, it will also knock over the P of 100. Then P of 100 will knock over the P of 101 and so on. So in this case, we want to prove that the sum of all positive integers from 1 to 100 is 100 times 100 plus 1 divided by 2. So this is the formula now. So we are now in our mathematical induction formula. So in proving that P of 99 will knock off P of 100. So again, we will use P99, P of 99 as our premise. And we want to prove that the sum of the positive integers from 1 to 100 is 100 times the quantity of 100 plus 1 over 2. So to start, we see that the sum of the positive integers from 1 to 100 is, so we have 1 plus 2 plus 99 and also plus 100. So simplifying the equation or the expression, so we have 100 times 100 plus 1 over 2. So if we solve, so this will be our answer. So we can see that we have here um, equality, so that they are equal. So what we've just done here is analogous to checking two dominoes in a line and finding that they are properly positioned. Since we are dealing with an infinite line, we must check all pairs at once. So this is accomplished by proving that the P of n is equal to P of n plus 1, which is true for all n that is greater than or equal to 1. So this is the formula. So by proving that, we can say that they are lined up. So look at P of 1 here. The sum of the positive integers from 1 to 1 is 1 times 1 plus 1 over 2. By that, we can see that P um, of 1 is true. So this now will set off a chain reaction. Since the P of 1 will set off the P of 2, so P of 2 is true. Since P of 3 will set off uh, since the P of 2 will set off P of 3, then P of 3 is true, and so on and so forth.
Now, let us proceed to a well-ordering principle. Well-ordering principle is one important property of natural numbers. Well-ordering principle is true only if we are considering natural numbers, but it is not true if we are considering integers, real numbers, the rational numbers, or the complex numbers. So, what is well-ordering principle? So, the well-ordering principle states that for any non-empty set of positive integers, there is a least element in that set. In other words, any non-empty subset of the natural number has a minimum. Remember that natural numbers are a collection of numbers 1, 2, 3, and so on, and we don't consider 0 as the natural number. Let us look in detail what is well-ordering principle. Let A be a set such that 1. A is a subset of a natural number, and 2. It is a non-empty. If we have this two property, then there is a natural number m such that A, the natural number is in the set A, and B, it is less than or equal to any element of the set A. In other words, it has a minimum. One of the most important concepts is that the minimum has to be in A. Now let us look at some examples and see how this well-ordering principle works. If we have the first example, which is a set, um, that is a collection of numbers 2, 6, 27, 29, and 40. By definition of the well-ordering principle, we could say that this example is a set of a natural number and it is a non-empty. Then the well-ordering principles assess that it has a minimum and the minimum is 2. For another example, we have a set of these numbers 25, 48, 56, 89, and 110. Again, it is still a set of natural number and a non-empty. So it has a minimum and its minimum is 25. So by these examples, we could say that these examples given are well ordered. Um, An ordered set is said to be well ordered if each and every non-empty subset has a smallest or least element. And that is for the case of the well ordering principle.
Hello, everyone. This time I am going to talk about the Archimedean property. Well, actually, this just states that if there exist two positive real numbers, suppose we have A and B, and there exists a positive integer, a natural number, which is n, it should be that when you multiply n to the other positive real number, we can denote it as A is less than n times B. So that's the Archimedean property. Moving forward, now I will be discussing the lower bound, the upper bound, infimum, and the supremum. So let's talk about each one of them. Now, first is we have lower bound. No, a lower bound of a set is an element for which all elements in the set are greater than that value. Okay? So suppose S is a set of real numbers. A lower bound for S is a number B such that that certain number B is less than or equal to X for all X element of your S, which is the set of real numbers. Okay? So, a set A that is a subset of B is bounded below if there exists a lower bound L that is an element of B such that A is greater than or equal to your L for all A element of your set. So we just defined the boundary, the lower boundary or the lower bound of the set, and we have also defined what if we define lower boundary using or lower bound using subsets. Next up, we have upper bound. So an upper bound of a partially ordered set is an element for which all of your elements in the set are less than that value. So for lower bound, all other elements are greater than. For upper bound naman, on the other hand, they should be less than that value. This value need not to be in the set itself. Okay, just take note of this statement rather. This value need not to be in the set itself. So suppose we have set S as a set of all real numbers. The upper bound of your set is a number B such that all elements of your set S is less than or equal to B. Okay, how about our what if? What if we deal with subsets? How do we describe an upper bound? No? A set A subset of B is bounded above if there exists an upper bound, small b, that is an element of your set B, such that your A, which is an element of your set A, is less than or equal to your B. So that, my friends, are lower bound and upper bound. Now, what about infimum and supremum? Okay? By definition, your infimum is the greatest lower bound. Pinakamalaking lower bound. That is, if a set is bounded below. All lower bounds are at most as large as the infimum. Okay? We are yearning towards limits, no? If you can imagine or you can look further. Okay? So infimum, suppose that A is an element, is a subset of R, is a set of real numbers. Now, if M is in R and it is a lower bound of A such that your M is greater than or equal to your M prime for every lower bound of M prime of A. So suppose your M prime is your lower bound. Then your M is called the infimum of A, or is denoted as M equals INF of A. Infimum of A. So what are the characteristics of our infimum? First, the infimum of a subset A, a subset of B, is an element of S, that is an element of A, such that, here are the characteristics, but we just base this on the definition that we have stated a while ago. First, dapat si A is a lower bound of, dapat si S is the lower bound of A. And if your L is a lower bound of A, then S is greater than or equal to L. Kasi nga, by definition, your infimum is the greatest lower bound. On the other side, we have the supremum. By definition, our supremum of a subset, A subset of B, is the least upper bound of that set. Balikan natin si infimum. Infimum, again, is the greatest lower bound. Supremum is the least upper bound of that set. That means na if we have a set A and A is bounded above, then lahat po ng upper bounds, all our upper bounds, are greater than or equal to our supremum. So suppose we have A subset of R, and it's a set of real numbers, no? If your capital letter M, which is an element of R, is an upper bound of your A, such that M is less than or equal to M prime, and M prime is your upper bound of A, then M is called the supremum of A, and it is denoted as M equals SUP of A, or supremum of A. Now, what are the characteristics of our supremum? Nabalikan natin kanina, the characteristics of our infimum should be lower bound, and if it is a lower bound, then it's the greatest of the lower bound. Now, here, it should be an upper bound, no? And most likely, if we talk about supremum, no, forgive me for this, but most often, it is denoted by capital letters. So here, in the characteristics, I just use S para naman, we have somehow, we can compare it with the characteristics of our infimum. So, again, the characteristics of your supremum are the following. First, it should be an upper bound of your A, or an upper bound of your set. Next, if something is an upper bound of your the same set, no, it should not be less than your S. Okay? That's your supremum. So if we draw, no, infimum, supremum, lower bounds, and upper bounds, we have this. So notice, I hope you can see my laser pointer. So notice here, this is your set A. The lower bounds of your A are these values over here. These are called lower bounds. Now, the greatest of the lower bounds is what we call the infimum of your A. Now, the upper bounds are here, no? This is the upper bounds of your set. Now, the supremum of your set is the least lower bound of that set. So I hope lower bounds, upper bounds, infimum, and supremum are all clear for everyone. No? So that's about it for our group reporting or group sharing. Thank you so much. And if you happen to have questions, feel free to like, comment, and huwag nilang kalimutan mag-subscribe. Thank you. This has been Brave Hearts.